So yeah, I'm trying to figure out it's I've got several options. One is the education pushing on, but I don't know if you want to move. It's kind of the issue.
Well, then you can do it after you're at school. It's a lot easier.
I guess that's true.
I wish I could just go to a case and be like, no.
You were doing one semester, yeah, the first case I did was a domestic violence case. That was not fun.
Yeah, we had 2 of those last week.
Yeah, I had battles between 2 lesbians. It happened this like a year and a half after. And they were also still living together. They were still they were still living together. And the defendant was actively defending the prosecution. And so it was like, there was no clear evidence. And then, of course, I hate to say it.
All right. So we will cover more about charge pumps and then move forward with the sample and hold circuit. So you can see the circuit diagram of the ADC. It looks like this. This is from last semester, and there's some minor issues that I have to fix it so I can get an updated version for you guys for this semester. But this is from the last semester. Most of the circuits and the timing circuits is fine. So you can see the sample and hold circuits in front of it. It has a V in, its analog input comes in, and here's a op-amp, it's a competitor, and the SAR block, and the R2R DAC, right, the DAC, and this is a D flip-flop. Whenever the data is ready, it kicks it out to the output over here, and then convert it back to the analog voltage to compare. Okay, that's the whole circuit diagram. And this is a timing circuit. It requires a lot of counters. And here's the internal circuit of the sample and hold circuit. We'll get into the details of this, and you guys will have to draw it in electric VLSI and simulate it, verify the functionality of it. So here is the paper published in 1999. But it was a very popular paper because of the sample and hold circuit was being used for so many different in so many different places, and it's an ADC design. Okay, for the other parts are not really different, but here is the schematic of the sample and hold circuit, and a bunch of other things as well. But you know, so this is the chip. That's a dice photo. I think it's from a microscope. I couldn't tell the size, but looks like it's somewhere around 1 milli, because the pads cannot be too small. If it's too small, you cannot wire bond to it. And if you can visualize it, which means it's already in the 50 to 70 microns already. So it's about 50 micron by 50 micron at least, or 70 micron by 70 micron. So it's in that scale. Okay. So you can see in that case, the chip, the die size is about probably 1 millimeter, maybe a bit less, but similar. Okay, similar. So you can see it was a pretty old technology. That's why one single ADC takes so much area on the die. Okay. Anyway, so that's where's the circuit from? So here's the circuit, and you can see the goal. Okay, the goal, it's gonna be sample, track, and hold. So the pulses, whenever the clock comes, here's the black one. Here is the sine wave, right? So the analog input, and these pulses are sampling pulses, and the red one is voltage being tracked and held. So you can see the output. This is the output of the sample and hold. Okay, so the output VL over here. That's the goal. Okay. Having that in mind, then we come back and design the circuit. why we need this whole thing to just do a very simple sample, track, and hold. It's really cool actually. So you can see here's the sine wave, right? I zoomed in. You can see the sine wave over here. Definitely, it won't be, because it's a digital kind of like a discrete output. It's not continuous like analog signal like the black sound wave here. It samples it. You can see the pulse when the pulse, the rising edge comes, right? So it was at here. It was held at here. But whenever that conversion is done, I start sample another point. So it getting sampled, right? And then starts tracking during this pulse. So you don't want this pulse width to be too big, right? You want this to be narrow because you want to sample this point, and it's just basically just wasting time. So this takes a little bit time delay. So eventually you can tell it doesn't need to be that wide as long as this pulse width here is a bit wider than right after this this point will be fine, right? So it samples it. It takes some time to charge up to this voltage. Starts tracking. So start tracking. Okay. So start tracking during this. Whenever this is on, it starts tracking. And once you pull this down to ground, this holds here. It's not changing anymore. It's not tracking. It's not being reset. It's just holding at this point. So actually, the voltage, analog voltage being sampled, is actually this point. Right? That's the analog voltage being actually sampled. And though you can see here is being held over here, and what's going to happen is your ADC will start working really hard after this point because it's a DC voltage. It's not changing. We'll do the conversion, right? So do the if you have an 8-bit, there will be 9 states. Remember the little circles? You have 9 circles, 9 states to finish the SAR algorithm, right? Eventually get a converted result. So that's the duration to do the conversion, okay? And then whenever it's done, you kick that 8 bits out by using this flip-flop array, right? There will be a clock like this one. I call it door clock, like a door. You kick it out from the door, and so it's available to the outside. So it's basically just a array of flip-flops, right? So all the data is on one side of the D side of the flip-flop. Whenever it's ready, you send the clock to the flip-flop at the same time. So the output will be the final converted result instead of all the intermediate states of the SAR diagram. Does that make sense? So that's how it works, the entire workflow of the SAR ADC's circuit. And so we need to design a sample and hold circuit like this to get this part done. So to make the DC voltage available at the VIN, so you can do all the following conversion, right? So it has to be held over here. So there are a lot of potential issues, and this circuit solves the problem for you. So first concept is it's called bootstrap circuit. Let me draw it for you. Show this figure here first. Yeah, it's easier. So the concept is that we are trying to make our VGS, I'm going to explain why, but we want to make our VGS a constant. So remember that square law equation here? It's I equals, what's that, KP, N is the nMOS, and width over length, and then VGS minus VTH N square, right? So if your VGS changes, the current changes, and the channel resistance of the NMOS or PMOS also changes. So we can model the transistor because there's a parasitic capacitance and all the rest of the circuit has capacitors. So it's actually causing that the channel itself has a resistance as well, has all the NWELs, there are parasitic capacitance as well. So it's actually forming, you can model everything like an RC circuit, right? And R seems to be changing. R is going to be changing if VGS is changing. So the way to understand this easily is that it's like a faucet, right? So if you turn on the faucet fully on, seems to be a smaller resistance in the channel. Okay? Because if you give a big VGS, you turn this fully on, and it's able to run run water through it easily, right? So if you model everything like an RC circuit like this, so R is going to change. So as R is changing, your time delay is changing. If I have a signal, analog signal over here, if I tie this point to VDD, right? Because this is changing and your VGS is changing. VD is not changing, but this is changing. So eventually your VGS is changing depending on your analog signal input, and you are getting a different time delay all the time. So eventually it causes distortion. It's called distortion of the sampled voltage. Why? Because you can imagine this one, you are expecting the same phase, right? The same analog voltage over here. But actually, if there's a different time delay, this point will give you this point. So this one reaches here at this time, but the next one, because there's a different time delay, probably it shrinks. It comes earlier than expected. You know what I mean? Because of the different time delay, right? So in that case, a very simple transmission gate, where it's called pass gate, just by using transistors, right? And you tie this to VDD with a constant voltage, will give you a distortion to the sample voltage at the other side, on the other side. And here, if we don't have that complicated circuit from the paper, right? Analog signal comes in, I got capacitor, like C sample. I turn on this one, right? I can turn on and off. I control this one from 0 to VDD. If I want to start sample it, I turn on this NMOS transistor and I sample a point to the capacitor, right? And then I read it out. I turn this off, it's being held over here. It's not changing because it's not being charged or discharged. So after it's getting sampled, it stays over there. I mean, it seems like this is a very simple sample and hold circuit. But it doesn't work well because of distortion, right? Because you don't have a constant VGS. You do have a constant VG, but not constant VGS because the S is changing. Okay? So the whole paper, the entire paper is about how to solve this problem. Okay?
Can I get one of those too?
I gave it to you, right? I didn't?
You get this one. So the circuit that we were given, this solves or like helps solve distortion?
No, the circuit you are given is a charge pump. It's the different one. It's a small. Yeah. It's a part of the sample and hold circuit. So knowing the background is very helpful. Then we come back to the charge pump. So here's the goal, right? Here's the goal, and you can see. Look at the paper really quick. How we can make VGS constant if you tie G and S with the VDD. That looks weird. We have never done that, right? You are not grounding your source. You are not grounding the cathode. Is that weird?
Yeah. That's a bit weird.
But how this could give you a constant VGS? Because that's a voltage source. You cannot change the voltage source. It's ideal source, right? If I tie here and there with the VDD, VGS will be VDD all the time. So what if you have a signal coming from one point here? What's going to happen? Are you able to pass it to the other side?
Won't it like add with VDD?
Yeah, it's going to add to VDD, right?
And then also
Where to add? So which one will add a VDD to it?
The source voltage. Yeah.
the source
So
voltage.
yeah, let me draw it for you. If you have this one connected to, again, so this VDD is not grounded, okay? You got a signal here, VS plus minus, right? Plus minus. That's the signal. It's minus plus, minus plus, So adding to it. So VG will be larger than VDD at some point. Okay. However, the largest voltage available on the circuit is usually just VDD as a digital circuit. How could you create the voltage which is larger than VDD? So yeah, so you need a charge pump, right, to create that thing. So that's why we are talking about charge pumps. We'll get into that point pretty soon. But now you can see that because I tied, even though VG is larger than VDD, but VGS is not changing. The square law equation only looks at VGS, so we are getting a constant VGS across these two terminals. Okay, so in that case, when S comes, it's just adding to this VDD, and eventually you got a larger VGS, and then eventually it holds the VGS as the constant voltage, which is VDD. So your VS is able to pass to the other side with the least distortion. So VS will show up on the other side. Any questions by far? Why VS can come through? Why? Because the VGS VDD is on, transistor is on, right?
Yeah.
So it's gonna pass. It's gonna pass through, and because you have a constant VGS, and it's holding this transistor being operated at a same state or same. I mean, I don't know if you've learned that in analog or not. It's being biased, right? It's being biased at the same operating point. So that's the analog voltage, analog terminology. But we don't have to talk about that for now. It's just same time delay for all the signal points, whatever the voltage is, right? So it's going to pass that one with the same time delay. So it's getting rid of the distortions. So that's a goal. So now the question is, how do we design a circuit you can tie a VD across it? Okay, so you need some sort of control, right? Cannot directly tie a VDD across the two terminals because it's gonna always keep it on. You are not always turn it on, right? You wanna turn on to sample and track and turn it off to hold. Okay, so you do need some circuit over there to get this job done. And if you come back to this one, and you can see that your VDD is definitely adding this shape of sine wave over here, right? Okay, so that's the goal, and this circuit will make that happen. So if I do a ideal circuit for this to implement this, it's gonna look like this.
So you have it hooked up to both ends of the charge pump. So the voltage doubler.
Yeah, if I label this VDD as switch 1, switch 2, switch 3. Okay, like this. So first, what you want to do is S1, S2, S5 closed. What is this doing? If S5 is closed, it's actually resetting this point. So whatever residue of the charge is stored over here at the gate because of the little capacitor over here, it will be discharged to ground. So first I close these two and this one. reset the gate. And also doing what? Charge up C1. C1 to VDD. And my question for you guys is, during this phase, is this little transistor, here's the VL, is this here's the analog V in, right? Analog V in. Is this transistor doing holding or sampling or tracking? I have a little cap here to store the charge. C storage.
I guess it would be holding, right?
It's holding, right? Why?
Because it's not changing because it's not active.
Yeah, because transistor is off.
Yeah.
Because this is grounded, so this guy is turning off, right? So you're not, V is not going through, so VL is just holding there because it's not able to discharge it. It's holding there, right? So this is holding there. And then if I do S3, S4, only these two closed. After this, after the first one, right, and do this, what's gonna happen? Definitely you wanna, so I'm saying these are closed, which means the rest are open, right? But I didn't include that, but the rest are open. So S3 S4 are closed, but the rest are open. So these are open, right? These are open. This is open, and and these are closed. What's happening?
C1 starts releasing its charge, right?
C1 was charged already, right? Because it was charged up to VDD. You got a floating VDD here. Keep in mind, it's a floating VDD. It's not grounded. It's not shorted to the source. It's a floating VDD, but it's okay. It's providing that voltage needed for the transistor to be turned on. So it's got a floating VDD, and these two are shorted. So you are applying that floating VDD to VGS. Okay, and then your signal can be added to that VDD. It's giving a constant VDD across the two terminals, and your VS can pass without any distortion. And that's gonna be sample and track, right? So that's the concept, and we need to design the circuit to get this done, right? Remember when we talked about the charge pumps last time? We were at here. And there's VD, and there will be a drop, which is VB. So I'm asking you, what's the VL over here? And what's the voltage at here? The difference. And this is from 0 to VD oscillation. So when this one was 0, right, when this is 0, it's going to pull current because the floating edge will pull current from VDD and to charge up the cap in this way. And that voltage will be VDD minus what? VB, right? And whenever this goes up, it's adding a VDD to these terminals, the two terminals.
Yeah.
Because plus minus, and this is grounded. So VA will be what? 2 VDD minus VB, right?
Yeah.
And then it's gonna and then this one has a floating edge again. We'll pull it down, so we'll charge it up to VDD minus VB again. So it's gonna oscillate between VDD minus VB and the 2 VDD minus VB. So these two voltages is gonna oscillate between these two voltages. If you draw a diagram, it looks like this. Right? It's definitely above 0. Okay, this oscillation is gonna be A, and then it's gonna pass this diode, and this capacitor is gonna serve as a low pass filter, and eventually, if you choose a relatively larger value of capacitor, this passes through, and then it's being dropped by another VB again, right? But the thing is, it won't discharge all the way down to VDD minus like 2 VB. But this one is going to happen. So you are getting 2 VDD minus 2 VB for the top voltage here. It's going to drop a little bit and won't discharge to the bottom because the capacitor is big. Will be a little ripple, but it's very similar to a DC voltage. That's how you can stabilize this one at a larger DC voltage value. And similarly, we could use NMOS transistors because all the diodes are pretty big in CMOS technology. So we hope that we can use transistors instead of diodes. And this looks very similar to the one I gave to you, right? So the circuit on the paper. And why this circuit can serve as a diode? Why they are very similar? So this guy, if you tie is the drain's gate is the source, right? If you tie gate to drain, you are guaranteed that this guy is operating at saturation mode. We covered this previously. And is able to run current from top to bottom. Okay, and there will be a drop from top to bottom if you have a VDD here. So the largest voltage you can receive at the source is what? Because VDD here as well. The gate is the same as drain, right? So both are VDDs. Is NMOS good at passing VDDs? No, it's good at passing zeros, but not VDDs. Because whenever this one, so for example, it starts passing it, right? Starts passing it. So the voltage here starts rising. Whenever it reaches what? It will shut this off. Whenever this guy reaches VDD minus VTHN, we'll start shut it off because VG is VDD. VS is VDD minus VTHN at this moment. So VGS becomes VDD minus VTHN, which is VTHN, which is required to keep this on, right? So that is why if this keeps going up, it will shut it off because it will not meet this requirement anymore. So this guy is able to pass VDD to the bottom. Is able to pass voltage from top to bottom, but it's losing something. So it's very similar to this guy, right? So the diode is losing a VB over here. So the largest voltage you can pass through this point is actually VDD minus VB. And this is a VDD minus VTHN. So they're very similar. They are both losing a little bit of voltage. And also the same thing is you cannot run current from bottom to top for this guy. Could you tell me why? I mean, this guy cannot run current from bottom to top because this is a cathode, this is anode. So diode only can only conduct current in one direction. So this is the same. So this guy cannot really run current from bottom to top as well. Why?
It's because two of the voltages are fixed, right? So even if you change the bottom voltage, you can never get it to run current backwards.
It's because the VGS, if you run current that way, and you are treating this one as. And VG and VS are the same voltage, so VGS is 0. It's less than VTHN. So you're not able to run current from bottom to top. So in that case, because they share the two common grounds, and that's why we can use this one as a diode, right? As a diode. So we replace that with a gate drain connected NMOS transistor and use it as a diode. So when this one is from VDD to 0, right, to 0, it's pulling down the falling edge. So it's charging up the cap with the voltage, which is VDD minus VTHN. Okay? Because whenever it's pulling down, it's a falling edge, will run current through here and charge it up because this is open, right? It's going to pull current to the capacitor. And if this goes up at a certain time, it will add a VDD to it. Okay, so this point A will change from where to where?
VDD minus VTHN to VDD minus.
Right, it's going to oscillate between these two voltages, very similar to the previous example. And then it goes through this one. It's very similar to the diode as well, as a low pass filter, and eventually you have this oscillator being filtered out, right, getting rid of the ripples, and so it was this. It's a VDD minus VTHN, 2 VDD minus VTHN, okay, and then it smooths it out. And the DC voltage is very close to 2 VDD minus 2 VTHN. Write it. 2 VDD minus 2 VTHN. Okay? And you can keep adding, you can add more stages to it in order to increase that voltage to a higher DC voltage. And that's a circuit provided in the textbook. It's called Dixon's charge pump. And it looks like this. So we need to find out the voltage oscillation at this point, at this point, and at this point. Maybe this point as well. Okay. And here. So we just simply, here's a clock, and we just simply invert it. Just invert it. That's clock bar. And let's see why or how this works. How this works. So here's a clock. Clock is just a 0 to VDD, right? 0 to VDD. So when this one pulls current from this guy, from the NMOS transistor on the top, A becomes what? When it pulls, it's a falling edge. When the falling edge, so charge it up, right? Charge it up. So that becomes VDD minus VTHN. and then it flips to the top. There's rising edge. This becomes 2 VDD minus VTHN. So it's gonna, so point A will oscillate between these two voltages, right? What about B? So when here pulls, here pushes, because it's getting inverted. So when this one pulls, it charged up, this one pushes, and this one doesn't have a switch, so it's not controlled. So whenever this one, the voltage getting here is actually being sent through this resistor and being sent to here, but with the reduction of the VTHN, one VTHN across it. But however, it's also adding what to it? If this is let's just give an example, okay? So if this is pulling, and this one becomes what? Becomes this, right? VD minus VTHN. If this is pulling down, right? Pulling down. So if this is folding edge, it's pulling down. All right. So this A is this, right?
Yeah.
And this is pushing.
Yeah.
And this is pushing. So it's adding a VDD to it.
So it'd be 2 VDD minus VTH.
Yeah. So whenever the voltage here is A is this voltage, passing this transistor reaching B is VDD minus what?
THN. Or
2 VTHN.
Yeah.
Because crossing this guy getting another drop of VTHN. However, this guy's pulling, right? This guy's pushing. It's adding one more VDD to it. So during this phase, you need a 2 here in front. You need a 2 in front of it. Agree with that?
Yeah. Yeah, because it's basically like additional. Yeah.
Yeah. So it's adding a VDD to it. It's pushing. It's pushing. Okay. What about the next? If this is pushing, and you are getting this voltage, right? And this voltage passes this transistor and reaching B is giving you 2 VDD minus 2 VTHN, right? However, this is pulling.
So well, the
Wait, this is pulling. If this is pushing, this is pulling. Yeah, I think that's it. Huh? It's pushing. So whatever voltage stored over here will be charged up, will be sent through this guy and charge up the capacitor and just giving you this voltage. Whatever the voltage is, it's going to be this voltage. Because this is pulling, right? This is a pulling edge. It's not adding anything, it's adding a 0 to it. Right, so the next one is this. Let me verify and see if this is right. I think so. Yeah, this must be right. Can't find the answer, but this must be right. It's just so simple, it must be right. Okay. So what about C? So we learned from the last example. We want to look at this voltage first, right? So this one passes this guy and reaching C is giving you 2 VDD minus 3 VTHN, right? And pulling, pushing, pulling. So it's not changing.
Wait, so B is not changing then? It's staying at 2 VDD minus 2 VTHN?
It happens at the same time actually. So whenever this guy getting charged up to this voltage, right? And this is the same thing, this is pulling at the same time. So actually this voltage will reach this point will reach this voltage, and then this guy will start pulling and trying to send that same voltage to this point. But however, it passes through this transistor, so it's getting one more drop.
I'm just trying to understand, is is B staying the same voltage throughout the clock cycle?
It's changing between these two voltages.
What's the difference between those two voltages?
Let me see.
Wouldn't it be direction?
Wait, so this, let me go through this one more time, just really quick. So if this one pulling, right? So if it's pulling, it's getting this, and this one is getting this one minus 2, and then it's adding a VDD because it's pushing at the same time. So this must be right, this one. And then if this is pushing, it was this, pushing, you got this. So this one passes through this guy, you're getting so this guy charges up to this voltage and passes through this one. It's going to be this minus this. This is passing this one more time. We got 2 times. It's pulling this down. Did I draw this wrong? Schematic? What is going wrong? Let me look at the notes I had last time.
B should have a capacitor. B's missing a capacitor. I think. Is it not?
No, I think schematic is right.
Maybe.
Let me look at this one. Let me look at the last semester's drawing here first, really quick. Here, right? It's the same schematic,
Oh yeah.
right?
Peak is an extra VDD
Hmm?
on the when it's pushing.
Oh, why is this guy drops 2 VTHN?
Yeah, that's right. It's the 3 VDD minus 2 VTHN. That's different. Which makes sense because it's magic. Well, because they're like stages.
Oh, it stays. Wait.
Well, aren't they like stages that go into each other? So
Yeah, that
they
makes
should-
sense.
And
So they
they
should do the same thing.
Yeah, because it's a charge pump, they should be increasing each stage by 1 VDD, but also decreasing them by an extra VTH.
That makes sense.
Yeah, it stays, right? So whenever this one got a 2 VD over there, it pushed again, you got a one more VD added to it.
Yeah.
Mm-hmm. Yeah, that's why. All right, thank you.
Thank you.
You.
It's hard to. It's
Yeah,
hard to
yeah.
read these.
Yeah. But are we good on the in class?
Yeah.
The in class is the one over here, right? This guy. So this is E there.
Still confusing.
So this one, and the first stage is very clear, right? It's
This
just
is an
changing
inverter.
between these two. Huh?
That's just an inverter.
Yeah, inverter in the front. It doesn't matter what the inverter is, right? But eventually you get a signal being placed over here. Why do we cover the inverter? It doesn't really matter, right?
Yeah.
It doesn't really matter. Just changing the phase, right?
Yeah.
Mm-hmm.
What is V to D? Input voltage.
VDD is the supply 5 volts.
5 volts.
Mm-hmm. Okay, so it's able to run in this way, and
Well, that would just be like the oscillating, like
like set DC, right? Because it coming in at a pulse,
Mm-hmm.
and since the pulse is inverted, it would just be. Wait, that would just be negative. That would just be a negative voltage, right?
Which one?
A
For this guy or for this guy?
for the one on the sheet,
Okay, this guy.
right? Because a capacitor gets charged up by the inverter,
Mm-hmm.
which is either giving 0 voltage or negative because it's inverted.
No, the inverter doesn't matter. It's just changing the phase. But
just
you're always feeding a 0 to VDD pulses to the input of this point,
Okay.
right? You don't have to worry about the inverter at all.
Okay. So,
Okay.
so yeah, A is just basically like the.
Yeah, it's just asking you what the voltage is gonna oscillate, what the range of voltages that oscillate, right?
Okay.
From where to where, for A and output, 2 nodes.
Thank you.
Mhm. So I think that's the schematic that I have over here. This is this guy. I simulated, it didn't show super accurate results, and this is using the C5 model. Okay, the C5 model is not exactly 0.8 volts as a threshold voltage, but it's very close. If you change the capacitor, so I think 10 nanofarads is a pretty reasonable capacitor, depending on the oscillation frequency over here. It's able to charge it up. And now let's run it and see what's going to happen over here. So there are some losses. If you see V in is just 0 to 5 volts oscillation, and this one is definitely being lifted, which makes sense, right? It's adding a VDD to it,
Yeah.
and it's getting very close to 10 volts. It's a VDD. Let's say if this is the VDD minus VTHN, and VDD is 5 volts, right? 5 volts minus VTHN is what? 4 point something volts.
Yeah.
So now let's probe here and see if this is 4 point something volts. Here, right? What's the voltage? 3.77. So it's a little bit lost here. It's not super accurate. 3.77. It's not 4.2 as we expected. And so let me rerun it. This. So here's the oscillation from VTHN. I forgot to probe the top. Let's probe the top as well. Let's see. So we're expecting 2 VDD minus VTHN, right? So 2 VDD will be 10. So 10 minus VTHN will be 4.2, right? I can see it's not exactly 4.2, it's 8.77 right here. Okay. I'm thinking, why is that? If I remove this part to reduce any influence from here, right? And I'm going to rerun it. See if this is more accurate. I'm going to probe this point. It didn't change it. So there are some losses. So then I'm gonna rerun this and undo it here, and now let's probe V out and see if we're getting a DC voltage. Run. V out. I feel that probably need to set up the models, the transistors width and length, to change it a little bit, because it seems like it's probably too small. Let me do it right now. Let's say 10 micro and 1 micro. That. So control right click, you can make this visible. 10 micro, 1 micro. let's do a 10 to 1 width to length ratio and see if this will help this a little bit. It goes up a little bit. Now let's keep doing that. So charge pumps really requires a pretty fat transistors per outlays because it's charging up the cap using the channel, right? So now let's do 100 micro. Okay, so we got enough current to charge up the capacitors. It goes up a little bit. Now let's probe this guy. Let's look at this one first. We're getting 9.8. 2 VDD minus 10 minus 0.8 should be 9.2, but now it's 1.8. And this one is 4.8.
Shouldn't it be 10 minus 0.2?
But the thing is, C5's threshold voltage is not 0.2. It's 0.5 or 6, I think.
On ours, I think it says.
Oh, yours is 0.2. Yeah. So yours is different. Yours is a 50 nanometer technology, not this guy. It's a different technology. Is it?
Yeah.
I think it's a 50 nano, right?
Yeah, it's
As a 1 volt as a VDD, right? 1 volt is VDD. So it's a different technology. So in that case, you need to use these numbers instead of the 5 volts ones. I'm sorry, it's a little bit confusing. So it's a different VDD and different threshold voltage. Okay? So you keep adding stages and it will be able to step up the voltage even further. And that's how the charge pumps work, right? Okay. And I think we'll talk about the sample and whole circuit from the paper on Wednesday because it takes time to draw the whole circuit and explain it. We are running out of time. So, and there might be a quiz on Wednesday or maybe Friday. It's part of the sample and whole circuit, not the whole thing, but part of it. I'm going to ask you how the voltage oscillates at certain points, but that'll be on Friday. So you don't have to worry about for now. Just pay attention on Wednesday during the Wednesday lecture, and it should be fine. Right? Study a little bit on Thursday. It should be fine.
I was gonna ask, how do you, so like on just like a regular capacitor, how do you tell like how much it decays down to before it gets charged up again from the pulse?
The value or the
Yeah, I guess like the value or like
how much you can tell if it's fully charged or discharged.
Yeah.
If it's fully charged, if you are driving it using a pulse square wave, you should be able to see it stops at certain points.
Yeah.
And it becomes flat, right? If it's not, it's always oscillating, which means it's not able to drive it efficiently.
Okay, so it shouldn't really oscillate enough to have like a.
Depending on application, right? For digital circuits, you don't want to oscillate it.
Yeah.
But for charge pumps, the low pass filters, that's the whole point. We want a big capacitor to not fully charge and discharge it, so it's becoming getting smoothed out. Okay. If it's being it's used as a filter, then you don't want to fully charge and discharge. It's digital circuits, you're trying to drive it, right, efficiently. You want to charge and discharge fully. Okay.